Over the last year I've built this robot. It's called Hexapod because it has 6 legs which are useful for walking in tough terrain. It can walk, dig, and even high five. There's gonna be a short version of this video on my main channel, but this is a deep dive. I'm gonna walk you through the whole process of building a robot. The mechanical engineering, electronics, and coding. I'm gonna show you all the mistakes and all the things I did right. If you are new and don't know what this or this is, that's fine, I'm gonna explain everything. And if you aren't new, there's still gonna be some more advanced stuff later, so you should get something out of it. Alright, let's build a Hexapod robot. At day 1 of the actual build, I had an optimistic view.
In the next 2 months, I'm going to build a Hexapod robot that's going to climb walls like a spider.
This estimate turned out to be inaccurate. Anyway, I started with a single leg. I'm gonna use these servo motors, which are basically a DC motor with a gearbox, which reduces speed and increases torque. This motor has 3 cables, 2 are for the power and 1 is for information. And if you're new to electronics, you might think you only need 1 cable for the power, but I'm gonna show you why you need 2. I'm powering up the servo with 7 volts, and if you connected it like this, nothing would happen, because you need a lower potential where the electricity will flow to. So I'm gonna add ground, which is 0 volts, and now the electricity flows from the 7 volts through the servo into the ground and delivers power to it. Okay, the servo is powered, now we somehow need to tell it to move to some angle. And that's what this third cable is for, the orange one. It carries a PWM signal, which looks like this, and it basically turns on and off the input voltage. And it's defined by duty cycle. So here the duty cycle would be something like 0.8, because most of the time the voltage is on. And here the duty cycle would be 0.5, because the voltage is half-time on and half-time off. And to encode the angle information, we could say that the duty cycle of 0 means the angle is 0, and if the duty cycle is 1, the angle is 180 degrees or whatever the max angle is. In practice, you don't need to know any of this. Just connect the servo to a supply voltage, ground, and a digital pin. Then you can set the servo angle in Arduino IDE and upload the code. Alright, we know how to use the servos, so let's design the leg. It's gonna have 3 of these motors. This is the minimal amount, because you need at least 1 motor per each axis it's gonna move along. The number of movement axes is known as degrees of freedom. This leg can move in X, Y and Z, so it has 3 degrees of freedom. And you can guess that the number of degrees of freedom is usually equivalent to the number of motors. We could also make it rotate around these axes, and then it would have 6 degrees of freedom, but for that we would need 6 motors, and that would be overkill. There are some weird examples where the number of degrees of freedom isn't equivalent to the number of motors. For example, this 2D arm has 5 motors. This tip can move in X and Y, and it can also rotate, so it has only 3 degrees of freedom, even though it has 5 motors. But usually for simple linkages like this leg, it's equivalent. I opened up Autodesk Inventor, which is a CAD software for 3D modeling. To model an object, you create a 2D sketch and extrude it. By adding and subtracting objects, you can model anything. After finishing my shitty model of the leg, I exported it as an STL file and opened it in Cura, which is a slicer program. Here you can choose the infill, layer height and other print settings. I set the infill to 20%, saved the G-code and started printing. For the material I chose PETG because I thought it's stronger than PLA, although harder to print. I glued all the pieces together and coded a basic movement. I coded the movement in angles, so the leg doesn't move straight. And I also fucked up the cat, so one of the axes is crooked. But that doesn't really matter because it was just a prototype. I was powering this servo with the Arduino 5V and ground pins, but now this leg has 3 motors and the Arduino doesn't have that many pins, so I used a breadboard. The breadboard has many pins connected together, so you can power them with the Arduino pins. Now these 2 lines are both powered, so this is the 5V and this is the ground line. And you can connect multiple motors to it. You're basically multiplying the Arduino pins. But the 5V Arduino pin has a maximum current of about 1 amp. So if you connect 3 motors to this power line, the current is gonna be divided. So each motor is gonna have a max current of 0.3 amps. And that might not be enough to power them, so you have to be careful with this. Also, breadboards are used for prototyping. They are not reliable, and later we'll upgrade to PCBs, which I'll talk about then. At day 5 I focused on the inverse kinematics, and I'll let past me explain what that is.
I built this one leg which is made from 3 servo motors. I can set the angle of each motor and the leg will move to some position. This isn't very useful since the movement is essentially random. What I want is to tell the leg to move to some position and let the robot figure out the angles. This is called inverse kinematics. I solved it by writing down the equations and transferring them into code. I can now move the leg in the X, Y, Z or any other direction I want.
Solving the IK involves drawing a bunch of triangles. If you want the whole solution, you can just Google Hexapod inverse kinematics. But here I'm just gonna give you the feel for it. We know this end position because that's the input, and we also know L1, L2 and L3 because these are the physical dimensions of the leg. However you modeled it, that's the dimensions. And our goal is to find motor angles θ1, θ3 and θ2. And for that we're gonna use Pythagoras and cosine law. So Pythagoras, if you have a right triangle and you know 2 sides, you can calculate the third. And with cosine law, if you have any triangle and you know all 3 sides, you can calculate any angle inside of it. We're gonna focus on θ3 right now. So I've made this triangle. And we can calculate L because it's just the Pythagoras. Now we have this closed triangle. We know all the sides and we can calculate θ3 with cosine law. We have θ3, we could calculate θ1 and θ2 similarly, but I'm gonna stop here. In practice, if you want an analytical solution, meaning you have a function that outputs the angles, you have to solve it by hand basically. But if you have a more complicated linkage, you can use numerical methods and optimization techniques and you'll get an approximate solution. I have IK as a function in my code, which translates the X, Y and Z into θ1, 2 and 3. So I can code the movement of the leg in spatial coordinates and the code translates it to the joint angles. Since I could easily code the movement of the leg, it was time to make the leg path.
So far I've built one leg which can move in the X, Y and Z axis. My aim is to combine these movements in a specific way which allows the robots to walk. I could let the leg trace out a triangle like this. The problem are these sharp corners. The leg is moving in one direction, and I'm telling it to move the other way the next millisecond. This causes the motors to overload. Instead of a triangle, I am using this smooth path which is called a Bezier curve. This curve is C2 continuous, which roughly means that the force acting on the leg changes gradually and not abruptly. This makes the leg movement smooth and doesn't wear out the motors.
So this is what the leg path looks like. There's a straight line at the bottom. This is when the leg is in contact with the ground. And then the leg lifts up and returns back to the starting position. This leg path is made from a straight line and 3 of these Bezier curves. I generated this curve in MATLAB and I saved the points, so the Arduino doesn't have to calculate this curve and just loads them. The reason I chose Bezier curves is because they are C2 continuous. So if this leg path wasn't C2 continuous, the acceleration of the motors could look something like this. So there will be a step change in the acceleration, which isn't great for the motors. And since this is C2 continuous, it means that the acceleration is gonna look at worst something like this. So it changes gradually, and this is generally better for the motors. The whole leg path has 100 points, 50 for the line and 50 for the Bezier curves. And this is because when the robot walks, it always has 3 legs on the ground and 3 legs in the air. So you want the leg to spend the same amount of time at the ground as it spends in the swing phase. Oh, one other thing. You might think that for this line you would need only 2 points, but that's actually wrong for 2 reasons. The first reason is that you would have no way of regulating the speed, because the leg would move as fast as the servo motors would let it. And the second reason is that this line is straight, but only in spatial coordinates. In a joint space, it's more complicated. Let's say you have this leg and you want to move it straight up into this position. And in both of these positions, this angle is 90 degrees. So you would expect it to move like this. But since this servo motor has the same angle, it doesn't have to move at all. And so what would happen is this motor would rotate and the path would be this circle. So if you want to move it in a straight line, you need to interpolate in between the positions. The position of the leg is defined only at those points. And if you want it to move in a straight line, you would have to do an interpolation. And the path in between these points could be something weird, but if you make enough of these points, it should be approximately straight line. At day 12, it was time to design the rest of the robot. By this time, I had already ordered another 16 servo motors. I buy almost everything from AliExpress, and this isn't sponsored or anything, I'm just gonna give you a quick tip. If you check this choice box and you buy stuff for $10 or more, you're gonna get free shipping and the stuff is gonna arrive in 2 weeks or less. I generally try to find the cheapest parts that are still decent, and all the parts I used for this robot are gonna be linked in the description. You don't have to buy it with my links, it just supports me if you do. The modeling took me 5 days, which sounds like a lot, but this assembly has 150 parts and they all have to fit together. This is the body of the robot where the electronics goes. And quick tip, you see this big flat surface? Don't do this. Make it 3D or at least add ribs so it doesn't flex that much. I had to redesign this part later. The bottom part has mounting holes, and the whole robot is 70 centimeters wide, which is quite a failure because I wanted to make it as small as possible, and now it barely fits through a door. Now I was just gonna wait for the motors and print the parts in the meantime. 34 days later, I was still waiting for the motors. You see, AliExpress ships the order to your country, this is fine, but from there it gets delivered to your home by a local delivery company. which means I'm fucked, because in my country, the delivery company is this piece of shit. So I was just praying it would get delivered sometime, because I spent $200 on the motors. At this point I also started making YouTube shorts, so the footage will be vertical for the next few minutes. While I was waiting, I printed the body and a single leg. I chose ABS because the PETG I tried before wasn't rigid at all, and ABS should be even stronger. I joined the parts together with bolts and square nuts because I didn't know that heated inserts exist. I was happy with how it looked, but it was really heavy. I redesigned the tibia, which is this part, to add a greater range of motion. I attached the leg to the front of the robot, so I had to rotate the leg path by 60 degrees. I did this by adding 60 degrees to the first joint, which wasn't ideal since it rotated the path around that joint instead of the center of the leg path. I was starting to lose all hope, but at day 62, 2 months after I had placed the order, the motors finally came.
I replaced the old ones, printed some new parts and assembled 2 more legs. I updated the code so it generates 2 more paths for the added legs. I tried powering it with a notebook, but the motors draw too much current, so I had to switch to LiPo battery already. The 11-volt battery is connected to a buck converter, which reduces the voltage to 7 volts, which the motors need. I also added a switch for the battery. Next, I will properly write a code for turning the robot while printing the remaining 3 legs.
Since the robot had 3 legs, I had to upgrade the power supply. Before I was using a notebook to power the Arduino, to power the breadboard, to power the servo motors. But the Arduino 5V pin doesn't have enough current to support 9 servo motors, so I switched to a LiPo battery. I was a bit confused when I bought my first LiPo battery, so I want to clear some things up. LiPo stands for lithium polymer, and these batteries are usually the go-to because they have high currents and high energy density. There are 2 main things you want to consider when buying a LiPo battery. The first thing is voltage, and the second thing is capacity. For the voltage, you're gonna find these batteries in 3.7 volt increments, and that's because how they are made. LiPo batteries are made from these 3.7 volt cells, and you can stack these up to create higher voltages. And this is what the S means in LiPo batteries. So let's say you will have a 2S LiPo battery. That means it has 2 of these cells connected in series. In series, these voltages add up and you get 2 times 3.7 volts, which is 7.4 volts. You could also connect these cells in parallel, then the voltage would stay the same, but the capacity and the maximum current would be double. I'm gonna use this 3S LiPo battery. That means the voltage is gonna be 3 times 3.7 volts, which is 11.1 volts. The voltages I talk about are minimal voltages. So if this battery is dead, it's gonna have this voltage. And if you charge it up, the voltage is gonna be higher. For example, a 2S LiPo battery has 7.4 volts when it's discharged. And when you charge it to 100%, it's gonna have 8.4 volts. And you can use this to check how charged the battery is. So if it's 8.4 volts, you know it's 100% charged. If it's 7.4 volts, you know it's completely dead. Alright, the capacity is expressed in milliamp hours, and this is a really useful unit, although I use amp hours usually. This battery is 2200 milliamp hours, which means it's 2.2 amp hours, and this means it can provide 2.2 amps for 1 hour, and it also means it can provide 1 amp for 2.2 hours. These batteries also have a C rating, which helps you calculate the maximum current the battery can provide. This battery has a C rating of 10C, and if you multiply it with the capacity, you get the max current. So the max current for this battery is 2.2 amp hours times the 10C rating, which is 22 amps. So if you're gonna power anything under 22 amps, it's good. And if you power something that requires 50 amps, the battery is gonna explode. There are 2 easy ways to destroy these batteries. One is to completely drain it. If it's dead and you keep using it, you're gonna destroy it. And the second way is to pull a high current from them, either by connecting something that requires a high current, or very easy way is to just short circuit these. So if I connected the ground and the 11 volt pins together with a cable, the cable has a very low resistance, so there will be insane currents, like thousands of amps, and the cable would melt and the battery would explode. To charge these batteries, you need a specific charger. I got this balance charger. It cost $5 and it can charge 2S and 3S LiPo batteries. And what the balance charger does is that when you have a 2S LiPo battery, you can't just charge it with a voltage like this, because then this one cell could get most of the voltage and this cell could be dead. So you need a balance charger that charges both of the cells separately. At day 95 I had made some progress and the robot was actually able to take his first steps. I was at the hospital for the last month, but I managed to assemble the remaining 3 legs. I wrote a code to make them move and tested it. Then I printed a stand for the robot, so I can test all of the legs easily. Since I finished all the legs, I let the robot take its first steps. The robot only walks forward. It has no control system or sense of the environment yet. It walks slowly and takes small steps, because I miscalculated the power requirement. I already ordered a battery with lower voltage, so I don't have to use the buck converter, which only provides 15 amps. The battery has plenty of power, but the buck converter has a maximum current of only 15 amps, which is barely enough for the robot to walk. The motors would also start moving randomly, or they wouldn't move all at the same time. At day 112 I improved the electronics. The old robot didn't have enough power, because I was using a high voltage battery with a buck converter which didn't provide enough current, so I had to redesign the circuit. I bought a 7 volt battery and connected it directly to the motors, so I don't need to worry about not having enough current. Next, I changed the breadboard for an Arduino shield, which lets me connect all of the motors easily. I also soldered a flyback diode and a capacitor on the Arduino for more stable power supply. Now the robot can walk faster and take bigger steps. In the next video I will write a code to make the robot run and maybe add a remote control joystick. Since the buck converter wasn't good enough and I couldn't find a better one, I had to figure out something else. I could use a resistor to make a voltage divider. With a voltage divider you have an input voltage and you can set the output voltage by choosing these 2 resistors. Let's assume that all the motors are just a one giant resistor Rm, and we want to pick the resistor R to lower the voltage accordingly. If these 2 resistors were both 100 ohms, the output voltage would be 1/2 of the input voltage. And if this resistor was 100 ohms and this one was 200 ohms, the output voltage would be 1/3 of the input voltage. So that's how this formula works. And this sounds great. We can pick any resistor R and lower the voltage however we want. But there's a few issues with this. The first issue is that this resistor dissipates its energy by turning it into heat. So not only are you wasting energy, but you also have a giant heater inside of your robot. The other issue is that all the motors aren't just a one big resistor. They have capacitance and inductance, and this creates an impedance, which is basically a variable resistance. So this is gonna behave differently than you would expect. The other option would be to use a 2S LiPo battery. The 2S LiPo battery has a voltage of 7.4 volts, which isn't that high, but that's the voltage when the battery is dead. When it's fully charged, the voltage is 8.4 volts, which is significantly higher, so this could damage the motors. The other issue is that it could also mess with the PID gains. If you have a motor and you want to turn it 90 degrees, this sounds pretty straightforward, but it isn't. This is kind of a stupid example, but let's say you wanted to turn this ruler by 90 degrees. You could do it slowly, and that would work, but it would be slow. Or you could do it really quickly. And then the ruler would overshoot and start vibrating. So you have to find a trade-off between speed and no vibrations. And that's what the PID controller inside of this servo motor does. The PID controller is defined by 3 constants, and they have been tuned to the motor's operating voltage. So if you input a high voltage, it's not going to be tuned well. And my guess is that since the voltage is higher, the speed is going to be higher, so the motors could start vibrating a bit. These options aren't great, but I decided to go with the 2S LiPo battery because it's the easiest. The sensor shield I added has the power, ground and digital pin next to each other, which makes it easy to connect the servos. The Arduino shield was better than the breadboard, but it still needed some upgrades. I added 2 upgrades, a bulk capacitor and a flyback diode. In this circuit I have a 2S LiPo battery powering a motor. You would expect the voltage of the motor to be just the battery voltage, 8 volts, but I have 18 motors here and they pull a lot of current, so the battery can't always maintain this voltage. Therefore the voltage is gonna have some ripple, and to get rid of this ripple and provide more stable power, you can use a capacitor. You can think of a capacitor as a battery that takes some time to charge and to discharge. In this example we have a battery and a switch which connects the battery to a resistor and a capacitor. If we look at the capacitor voltage and flip the switch, the battery voltage isn't gonna jump straight to the capacitor, it's gonna take some time to charge up. So at first the capacitor voltage is 0, and then it rises to the battery voltage over time. Now if we took this capacitor charged to the battery voltage and put it in a new circuit with a switch and a load resistor, at the start the capacitor has the battery voltage, and then when we flip the switch, it's gonna discharge to the resistor, which is gonna dissipate the energy in heat. So as you can see, the capacitor takes some time to charge and discharge, and we can use this property to filter out the battery ripple. And this circuit, where you have an input voltage, a resistor and a capacitor where you read the output voltage, is called a low-pass filter. Low-pass filter means it lets low-frequency signals pass and blocks high frequencies. So in this example, when we flip the switch, the voltage jumps to the battery voltage from 0, which is a high frequency signal, so it resists the change for a long time. But if we increase the battery voltage over time, the capacitor voltage could be very similar. Low-pass filters are widely used in electronics. You use them to filter out noise or to power a more stable power supply. The second upgrade I added was a flyback diode. We have a circuit with a battery and an inductor. When we close this switch, there's gonna be a current flowing from the battery to the inductor. The inductor is a coil of wire, and when you pass a current through it, it creates a magnetic field. This creates an electromagnet, and these inductors are inside of motors. That's how the motors work. Now when we open the switch, you would expect the inductor to just lose all the current and all the voltage, but that's not how it works, because it has accumulated energy in its magnetic field and now it has to dissipate it somehow. So there's still gonna be a current flowing, but now since the circuit is open, it has nowhere to go. So there's gonna be a huge voltage spike across this inductor, which can cause sparks over the switch. Or worse, if you control the switch with an Arduino, the spark can go through the Arduino and destroy it. To solve this issue, we can add a flyback diode. A diode lets current pass only in one way, so before it was doing nothing, because the current was flowing through the inductor back to the battery. But now, since we have this closed loop, the current flows from the inductor and discharges to this diode. So the energy from the collapsing magnetic field is dissipated into the diode. and this protects the switch and the Arduino. In general, when you have a DC motor powered by a battery, you can add a capacitor and a diode for a more stable power supply and to protect the circuit. This is what a capacitor looks like, and this is what the diode looks like. Although I used a Schottky diode, which looks like this. After day 112, I encountered some major issues and stopped recording the progress on YouTube. I even considered not finishing the robot, which brings us to this 200-day pause. Pretty much from day 1, I was working on a remote controller behind the scenes. I bought NRF24 chips and a HC05 in case the NRF didn't work. I assumed this was gonna be pain, but I wasn't prepared for what was to come. After weeks of work, I managed to make a transmitter with an Arduino Uno, 2 NRF chips and a joystick. Schoď tu tlačku. Pořádně. Plnou parou vpřed, dělej. To se nezničí, ne? Since I could control the robot remotely, I also coded a simple turning sequence where the legs on one side moved in the opposite direction. As you can tell, the RC didn't work, the plastic feet slipped, and the turning sequence wasn't ideal. Despite this, an even bigger issue arrived. This is the sensor shield I'm using. It has a terminal block where you input the battery's ground and voltage. It powers the ground pins, the VCC pins by 8 volts, and it has digital pins which are connected to the Arduino. The Arduino's ground pin is connected to the sensor shield's ground. The 5-volt pin isn't connected to anything, and the VIN pin is the voltage input pin, so you don't have to use your laptop to power the Arduino. You can just use the ground and VIN pins. The VIN pin takes in 6 to 20 volts and it's connected to the VCC pin of the sensor shield. So this is great. With the battery we can power not only the servo motors but also the Arduino. Or at least this is how I thought it worked. In reality, the VIN pin isn't connected to anything, and the VCC pin is connected straight to the 5-volt pin. So all this time I was powering the Arduino's 5-volt pin with the 8 volts from the battery. This fried the Arduino over time. This was a setback for sure. I looked for a shield which could power 18 servo motors at 8 volts, but I couldn't find one. I could have made my own shield, but Acer, who is building this robot too, has already made a shield for his Hexapod. So I just downloaded the files from his Discord server and ordered the PCBs. Thank you, Acer. Oh, by the way, I'll get to what PCBs are later because I ended up designing one for the remote controller. Since the PCBs came from China, they went through our local delivery company again. They had arrived a few weeks before Christmas, and the staff told me they don't have enough time to find my package, so they took my number and said they would call after Christmas. Nobody called, so I went to the post office and they told me they had shipped the order back. So not only did I waste 6 weeks waiting for my order, I had to buy the PCBs again because the cost of reshipping was somehow higher than just buying new ones. Now I had to wait another 2 weeks on top of the time I had already wasted. I tried to file a complaint through their website, but it was broken. I wonder why. I found a guy who was responsible for dealing with this stuff. I emailed him and even got on a call with him. I explained the situation and he was like, "Yeah, that sucks. We can't do anything unless you sue us or something though." So yeah, anytime I order something now, I'm not sure if I'll get it in time or if I'll get it at all. Great service. After 2 weeks, I finally received the new package. I soldered and connected the Acer's PCB. It was the same as the sensor shield, but better, because the battery voltage goes into the VN pin of the Arduino. The main purpose is still to make the wiring easier, and again I added capacitors and a flyback diode. The robot worked the same as before, but now it could walk faster without burning the Arduino. To prevent slipping, I added this white foam, which worked, but the foam wore off over time, so I switched to a black foam seal, which was more durable. Nothing was burning now, so it was time to update the code. I added crawl mode, where the robot can move in any direction, but the body isn't running. This is the leg path which the tip of the leg follows, and from the top it just looks like a line. This is the robot from the top, and each leg has its own leg path, so right now the robot could walk forwards and backwards. If I wanted the robot to walk to the right or 30 degrees to the right, I would have to rotate each of the leg paths around the tip of the leg. For this I wrote two functions. The first one rotates a point around the origin. You can do this by just multiplying the point coordinates by a rotational matrix. And if this says nothing to you, don't worry, it's pretty easy, because once you write this out, you get these two simple equations, where gamma is the angle you want to rotate the point by, and x and y are just the point coordinates. So with these two equations, you can rotate the point around origin, and since the leg path is just a bunch of points, this also rotates the whole leg path. If you look at my robot, I want to rotate the leg path around the tip of the leg, but the way I calculated my inverse kinematics, I have my origin at the body, so I need to rotate the leg path not around the origin, but around this point, and for that I wrote this second function. This function uses a pretty cool trick. Since we know how to rotate around the origin, we can just move the origin to the pivot point. We can do this by subtracting the pivot point coordinates. After that, we can just use the rotational matrix like before, and after the rotation is done, we just add back the pivot point coordinates to translate the origin back to where it was. So we take this origin, we move it to the pivot point, we rotate around the pivot point, and then we move the origin back. This way I can rotate each of the leg paths around the tip of the leg and change the direction of the whole robot. At this point I started having some mechanical issues. The lower body was bending a lot, so I had to reprint it. I had printed the whole robot from ABS, which is a terrible choice if you don't have a 3D printer with a heated enclosure, because as the ABS cools, it shrinks a lot and the 3D printed layers don't fuse together well, so the final part is gonna break easily. And it also isn't too rigid. I printed the new lower body from PLA and also redesigned it to be more rigid, although I may have overdone it because it was really heavy. I used heatset inserts for all the bolted joints. If you didn't know, a heatset insert is a nut. You heat it with a soldering iron, press it into a plastic hole, wait for it to cool off, and then you can screw bolts into them. These make strong bolted joints. I printed a new upper body, also from PLA, with holes for the servo cables, because the old design didn't have these holes accessible. Then the legs started falling off, so I reprinted all the tibias. With the newly printed parts, I was able to ramp up the speed and get a decent performance. I like the step he makes at the end. The remote controller stopped working completely, so I switched from the NRF chips to a 433 MHz module. This worked better, but it was still shit, because most of the time it didn't respond. It worked only sometimes and only on a few meter distance. The robot started breaking down again, so I reprinted all the mechanical loaded parts, which is like 90% of them. If I knew I would have to reprint the whole robot, I would have redesigned it. I also printed a new stand for testing the robot. I got to a point where the robot was kind of working, apart from the remote controller, so I did some more coding and created a video showcasing the upgrades. When I made this video, the remote control stopped working completely, so I was forced to hardcode all the movements, which was very annoying. I added a ripple gate. The gate I used to this point is called tripod. It's where the robot has 3 legs on the ground and 3 legs in the air, and each leg is offset by half a cycle. With the ripple gate, the robot lifts the legs one by one. This makes the movement look more spiral-like and, in my opinion, creepy. The next upgrade I added was body control. The robot's body has 6 degrees of freedom, because it can move in X, Y, Z, and it can also rotate around these axes. So you get pitch, roll, and yaw. The translation was pretty simple. If I want to move the body up, I just move the legs down. So I take the distance I want to move the body up by, and I subtract it from the legs position. The rotation was more challenging, but it still wasn't too bad. I assumed that the legs lay on a plane, and I rotated the plane in the opposite direction I want to rotate the body. I calculated the height difference, and I added to the legs position. Even more, I can rotate this plane, and if I rotate it by 90 degrees, instead of pitch, I get roll. And what you saw in the video is I made the plane spin at a constant speed, so the robot was wobbling. I wanted to hook this to the joystick, so I could walk with the robot and wobble at the same time, but I was out of luck because of the RC. The last upgrade I added was turning. I was able to code the robot to walk around in a circle of any radius. This is how I derived the equations. So this is the robot from the top. These points are the legs of the robot. This origin is the center of the robot. And these arcs are the leg paths from the top. As you can see, the leg paths are no longer lines, but they are circles. There are 4 circles in total, and they all share a single point, which, as you can guess, is the center of rotation. So right now, this robot would walk around in circles around this point. One thing to note is that all of these arcs have the same angular size. So if this one was 40 degrees, this outer one would be 40 degrees too. This one is just longer because it's on a bigger radius. At first, I divided this problem into 2 sub-problems, inner and outer legs. This is the triangle I created for the inner legs. This is the center of rotation. This origin is the center of the robot's body. And this point is the midpoint of the arc. By doing some maths, I derived the x and y coordinates of the midpoint of the arc. By changing theta according to this equation, you sweep out the whole arc. This triangle defines this left upper leg, but you can change this angle to define the 2 other legs as well. So if the angle was 0, this triangle would be a line, and it would correspond to this left leg. And if the angle was minus 60 degrees, it would be this left lower leg. The equations for the outer legs turn out to be the same. The x is just flipped because I flipped the coordinate system. What's nice about this is we can choose any turning radius, and my original plan was to hook the turning radius to a joystick, so it would be like steering a car. If you move the joystick to the left, the robot would start turning to the left, and the more you moved it, the more the robot would turn. Unfortunately, I didn't have a working RC, so I just coded the robot to walk around in a circle. Since I finally had something to show, this marked the end of my 200-day pause, and I started recording the progress on YouTube again. I even managed to get the remote control working, but ever since I made the robot stiffer, the legs started vibrating. So this was the focus of my new video at day 377. This is my robot I've been working on for the past year, and I'm getting pretty close to finishing it. But it has a problem that when it walks, the legs just start vibrating like crazy, and he looks like he's about to give a presentation. I tried fixing this by adding a cap which adds friction to each joint so it vibrates less. But the caps aren't strong enough, so they just fall off after a few minutes. So that's the issue I'm gonna solve today. This is a part of the leg, and this is the cap which adds friction to this joint. It is bolted to this part above it, and this cap cannot rotate, because if it did, it would just unscrew the bolt and fall off. So to stop it from rotating, I added this square peg, which fits into a square hole, and this constrains the movement. The issue I'm having right now is that this square peg is too small, so it just snaps and then the cap falls off. This is the old cap, and I know it's tiny, but the reason I designed it like this is because I didn't want to redesign other parts. But since it snaps off, I have to do it anyway. And with this part redesigned, I need to make this part bigger and this part bigger as well. I'm not showing it here, but I have to disassemble the whole leg just to change these 3 parts. It takes about 20 minutes, and eventually I'm gonna have to do this for all of the legs, which is 6 times, so it's gonna be super painful. After changing the leg, I let the robot walk for about 10 minutes just to test out the new cap, and it works real well. The old caps fell off and the new one is still attached, so I'm gonna change all of the legs. I built this robot just for fun, but I think it could actually be useful because it can navigate in tough terrain and climb hills. But this robot has another problem. These feet are terrible. They dig into the ground and they also slip. I originally had a piece of foam seal at the end, but it wasn't strong enough, so it just broke. What I want to do is to snip off the tip of the leg and glue a new tip on the leg, which is gonna have a sphere of silicone at the end, so that should get rid of the slipping. I just printed a new tip for the leg. It has a sphere at the end and I'm gonna cast a silicone sphere around it. This should provide better traction and decrease the load of the motors. I'm just playing with the dimensions right now, so this is the third and hopefully final prototype. This is the mold I printed, and you can see that when I take the tip of the leg and click it into place, it holds it at the center of the mold. The idea is that I'm gonna take these 2 parts of the mold and bolt them together. I'm gonna fill up the mold with silicone, and then I'm gonna click into place the tip of the leg, so there should be no bubbles in the silicone. The silicone is made by combining 2 parts, A and B, and I just realized that my part B is hardened, which it shouldn't be, so I'm just gonna dilute it in some alcohol and see if it works. So, as I said, I'm just gonna crush the part B into powder and this will definitely work. It looks like it's getting solid, so I'm gonna pour it into the mold and hope for the best. The silicone still isn't solid. I think the part B is just dead. It probably underwent some reaction and didn't just dry up. So I'm gonna order new silicone and finish the legs in a week or so. With the vibrations sorted, I wanted to make a remote controller. So I made a prototype at day 393. I've been making some serious progress on my robot, although I haven't upgraded the remote control yet. This is mainly because it's perfect, but I'm gonna make some minor adjustments nonetheless, and with them the robot should be able to do some interesting stuff. So this is my current controller, and I know what you're thinking. Why isn't it in that beautiful plastic cap? It's because I added this slider and hooked it to the height of the robot. So when I move the slider up, the robot lifts from the ground, and when I move it down, the robot crouches. I'm gonna add more buttons, joysticks and make an actual controller. But before that I need to change something. Since my last video I changed all of the friction caps so the legs don't vibrate as much. But now the Hexapod doesn't fit onto the stand because I increased the size of the coxa joint. Since I've increased the size of the coxa joint, this gap doesn't exist and these arms have nowhere to go, so I'm gonna make them shorter. The arms are now shorter, so they don't need this gap at all. The stand is fixed, so let's make the controller. First I made a sketch on my new whiteboard I got recently. Then for each of the controls, like the joystick, the switch, the sliders and the button, I printed these attachments. When you print stuff, the plastic always expands and shrinks, so the dimensions change. Therefore, I always print smaller sections of the final part to get the dimensions right, and then at the end I print the whole part. I modeled the full controller and now I'm gonna slice it in Curve, which generates the G-code for my 3D printer. But before I do that, I'm gonna show you the power of bigger nozzles. With the standard 0.4mm nozzle, this print takes about 7 hours. And when I change it for a 1mm nozzle, it takes only 3. Just as I started printing the controller, the silicone I ordered in my last video finally came, so I can finish the feet for my robot. The molds are made from 2 pieces bolted together and the plastic tip of the leg clicks into place. The silicone is made from parts A and B. Part B is 2% of the mixture, but how the fuck do you measure that? So I'm gonna put more, and this should also make it solidify quicker. The feet should be solid in an hour or two, so let's assemble the controller. Both of the joysticks are bolted to the base plate, the 2 sliders click into place, the button is bolted, the switch and the battery click into place, and there's a breadboard in the middle. Alright, the easy part is done, now I'm gonna wire up the electronics. I've just connected the battery through a switch to the Arduino, and I'm reading its voltage through a voltage divider, because if you drain the battery, you basically destroy it. The battery is at about 12 volts right now, and I thought about adding a capacitor to smooth out the readings, but the waveform is already smooth, so I don't need it. I also added an indicator light for the battery. Now it's blinking because the battery is turned off, and this indicates a low voltage. When I turn on the battery, the light stays on, and this indicates that the battery is sustainable. So in practice, when I turn on the controller, the battery is gonna be on, and if the voltage gets too low, it starts blinking. I've just connected this button, and it's gonna control the gates of the robot. So there's a counter in the code, and when you press this button, it increases the value of the counter by 1. And each value is gonna correspond to a gate, which is basically the movement type of the robot. And by pressing this button, you're gonna cycle through these gates. So this is the value of the counter, and you can see that when I press it, it always increases by 1. and then it overflows. And sometimes when you connect buttons like this, you get a problem called bouncing, which is when you press the button once, but it sends a few signals, and this is due to the mechanical vibrations of the button. I don't have this problem, so I didn't have to do any debouncing. The sliders have been added. I actually connected them wrong at first, so I blew one up, but fortunately I bought 3. And here you can see the value of the slider. I've just added both of the joysticks and also the transmitter, and now this thing is basically done. You can see that when I move the joystick, it tracks its movement. It goes up and down, and now it's time to do the hardest part, which is connecting the transmitter to the receiver. If this isn't the best looking controller you've ever seen, I don't know what is. After a few painful hours, I managed to connect the robot to the transmitter. So I'm gonna take him outside and see how he walks. But before that, I'm gonna attach the silicone feet. Alright, let's see how he walks with his new feet. So the robot took one step and the feet immediately fell off. Well, there goes 10 hours of my life. At least my dog likes them. Hopefully we'll have better luck with the controller. You control the movement of the robot with the right joystick, and with the right slider you control the height of the robot. If you move the left slider, you control the radial distance of the legs. And now I'm gonna change the gait, and you can see he walks differently. He lifts the legs one by one, and now I've changed it back. Before I give up on the feet, my girlfriend suggested I use super glue. I'm not sure how well it holds on silicone, but I'm gonna try that, and hopefully I won't glue my fingers together, because that's what happens every fucking time I try to use this. And of course I spilled the glue on my finger. If it sticks to the feet as well as it sticks to my finger, I think this should be alright. Alright, I'm gonna glue the rest of the feet, but with a key difference. This time I'm using gloves. Now I'm just waiting for the glue to dry, and I didn't bother recording the gluing because I was too busy not spilling the glue on myself. But he looks like a flower, it's kind of funny. To test the new feet, I built this obstacle course. And the robot has to tug his feet in, so he fits in between the skateboard and the chainsaw, of course. And then he was supposed to traverse this mountain made out of shoes, and he broke his leg. After shedding a couple tears, I took the leg apart, and fortunately it wasn't a broken servo motor, it was just a loose bolt. So I tightened it and put it back together. Finally, I just played with the robot. I put a 5-liter water bottle on the ground and let him walk over it. I even tried balancing him on the top of the bottle. So yeah, this robot is starting to be real fun. The new controller works. The next step is to make a new controller with PCB. That's gonna look even better, if you can believe it. At day 444, I added the most exciting update yet. Robots are everywhere. They build our cars, save lives, and even explore distant planets. Well, this is my robot, and it's pretty useless. So today I'm gonna take all my engineering knowledge and teach him how to high five. Have you ever wondered how this robot walks? I mean, each leg moves in a straight line, so the robot goes forward, and then it lifts up and returns to the starting position. But how do you explain this to the robot? So this is the leg of the robot. It has 3 motors, and what you can do is to rotate each motor by some angle. And the leg will move to some random position. But what if you wanted the leg to follow this curve, so it actually makes the robot move forward? Well, then you want the exact opposite, because this curve is defined in spatial coordinates. So we want something that when you input the spatial coordinates, you get out the angles. And the function that calculates this is called inverse kinematics. Don't mind this leg, we'll get to that later. So instead of setting these angles and letting the leg move to some random position, I tell the code to move the leg, let's say 50 millimeters that way, and the code calculates these necessary angles. To generate this curve, I wrote a code, and I saved all of the points of the curve. I'm feeding these points to the robot, and the robot calculates the necessary angles. But what if I wanted to do more advanced movements? Like, what if I wanted to tilt this robot, or make it do high fives? I would have to write a code that generates curves for each of the legs. And I could do that, but I have a better idea. This is Blender. You can do many things with this program, but I'm using it for animation. So I've made this animation, and then I wrote a script that saves the positions of the legs. And when you run the script, it generates this text file with all of the positions, and it also generates this bit of a code to make my life easier. Then I just take this and paste it into my main Arduino code, load it to the robot, and it does exactly what the animation does. So instead of generating curves for each of the leg, I just do this animation and then I paste it into the main script. And you might think that if I wanted to rotate the body, I would need to save its position too, but the 6 positions of the legs actually completely define the movement of the whole robot. And this took me like 5 days, but now it would take only 20 minutes. This was my first time working with Blender, and I want to show you what I did roughly to get to this point. I started by modeling the robot's leg. I modeled each link on top of each other, and I've put in the exact dimensions the physical robot has. This is really important. These are just objects and they don't move, so you have to add armature, where you define how the objects are linked together. With the armature, I was able to add inverse kinematics. I chose the tip of the leg to be target, and with a few clicks I was able to move the leg and have Blender calculate the angles. With the leg finished, I modeled the robot's body and parented the leg to the body. After that, I copied and pasted the leg 5 more times, and then the robot was finished. With the robot modeled, you can keyframe the location, go a few frames in the future, move the robot somewhere, keyframe it again, and then when you play it back, the robot moves. After I transfer this to the real robot, I noticed that there's a difference between the real robot and the simulation. For example, with this sitting animation, I have to tilt the robot's body in Blender just to make the real robot have 0 tilt. I triple checked the physical dimensions and it seems to line up with the simulation, so I'm not sure where this error comes from, but it's really annoying because I wanted to code a whole dancing sequence for the robot, but it would take too long because with the error I have to check each movement in real life, which takes up a lot of time. So just to recap, I rotate the robot in Blender. The Blender generates the spatial coordinates, which I paste to the Arduino. And the Arduino calculates the inverse kinematics and outputs the angles of the motors. So I control the animations of the robot with this controller. And don't be fooled by the beautiful design, it's actually pretty shit. It only has one button and I need at least 3. So I'm gonna upgrade the controller and then I'm gonna make him high five. Do you see this mess? PCBs let you transform all the ugly wiring into a nice little circuit board. At first I didn't know what the fuck a PCB is, but when I found out, it turned out to be simple and very useful. Let's say we have this simple circuit with a battery and a capacitor, and we want to filter out the battery voltage. If we wanted to make this circuit into a PCB, we could use pin headers to plug in the battery and to take the voltage out. And in between them, we could use this capacitor. To connect the components to the PCB, like this capacitor, we need 2 holes in the PCB. We plug the capacitor in, and then from the other side we solder it to the PCB. This makes an electrical connection. After you're done making the schematic in your software, you need to assign footprints. The footprints are the physical dimensions of the holes and the padding of the components. The padding is a thin layer around the holes where you put the solder. This is what the footprints for the pin headers look like, and this is the footprint for the capacitor. After you're done assigning all the footprints, you can start making traces. Traces are the electrical and physical connections of the different footprints. Most PCBs have 2 layers. You could make all the connections you can on 1 layer, and then when you run out of space, you make the rest of the connections on the 2nd layer. And even then, if you run out of space, you can use something called vias, which connects the 2 layers together. So if you had a trace you couldn't pass, you can use 2 viases to create a bridge. Usually you want to have a ground layer where you have only ground connections, and then on the 2nd layer you create the rest of the traces. 2 things I want to add. The components are either THT or SMD. THT stands for through-hole technology, so the components go through the PCB and you solder it from the backside. SMD means surface mounted device. If you had this chip, you would just place it onto the PCB, put soldering paste onto the pins, melt the soldering paste with hot air. This would melt the tin and attach it to the padding. The second thing I want to talk about is the copper layers. So this is the cross section of the PCB. You have an insulator, and from both sides is coated with copper. If you wanted to make this trace, you could machine out everything that is in the trace, but this would be a huge waste of time. So what they do instead is they just machine out a border around that trace, and this saves a lot of time because you only need to machine that small border. That's why when you look at the traces on the PCB, each trace has 2 lines, and the 2 lines are the border. I designed my PCB in KiCad. It was a 3-step process. First, I opened up Schematic Editor. This is where I made all the connections. This is the Arduino Nano. It doesn't have to look like the real thing, this is just to define the connections. For example, this is the VN pin, it's connected to 12 volts. And this is a pin header where I'm gonna connect the battery. And it's also connected to the 12 volts, so these 2 are gonna be linked. After I connected all the components like the joysticks, the sliders and the buttons, I assigned the footprints. Some of the footprints, like the pin headers, are in the library, but if you want something more specific, you usually have to create the footprint yourself. This is quite annoying, but once you do it once or twice, it doesn't take that much time. After I assigned the footprints, it was time to open up the PCB editor. This is where you define the dimensions of the board, and you can choose the layers and make the physical traces. And since we defined all the connections in the schematic editor, this forces us to not fuck up. For example, these 2 pins are linked, and I can't connect this pin to anything else. After you're done making all the traces, you can view your PCB in the 3D viewer. And then you just export the Gerbil files and send it to a PCB manufacturer. These helping hands are great. Man, I hate soldering, but this is cool.
Dope.
Nice. Alright, let's make some animations. For the high five, he just lifts up his leg, waits for the hand, and then executes the high five. Now, this robot has 6 legs, and each leg has 3 degrees of freedom, X, Y, and Z, so that's 18 vectors. And these 5 legs aren't moving, so to save space, my code ignores them, which is why the vectors have only a single element. Okay, so now I want to make the robot dig. So at first he's gonna sit back like this. And then he's gonna dig into the ground with his 2 front feet. Okay, so this is the first animation, he just sits. And now I'm gonna make a second animation where he's actually digging with his feet. Okay, that's it. I'm not gonna animate the second leg because it's just the mirror of the first one. And this is again to save space. Now in the Arduino code I just pasted the animations. And I have these 3 states: sit, dig, and high five. And to go from one state to another, I'm using a switch case structure. So when I press the sit button, it's gonna activate state 20, and it's gonna execute only this part of the code, which is the sitting animation. And then when I want to go to the dig state, I just press another button and it's gonna execute the digging animation. And this type of programming is commonly used in embedded systems, and I've also programmed this robotic arm the same way. Alright, let's have some fun. It's been a long journey, but we have finally reached the end. These are the most recent clips I filmed when I took the robot shopping at day 440. This was my first time using an Arduino, 3D printing, and generally building a robot. It took over a year to build, and apart from some exceptions, I really enjoyed it. I planned to do so much more with the robot, but after some consideration, I decided it was time to retire it. I'm gonna make a video on my main channel explaining why. Now let's zoom out. Look at the biggest challenges and what I would do differently. Wireless communication. This was the biggest bottleneck of this project. I spent so much time on it that it hurts to talk about. The best I got was an RC that occasionally worked within a 2-meter range. I tried many things but never got it to work. I'll try using ESP now for my future robots, since I've heard it's not completely shit. Weight. The robot weighed 5 kilograms, which is 2 kilograms more than I had planned. ABS. I had printed the robot in ABS, which prints terribly on Android 3. This paired with the higher weight resulted in mechanical failures of almost all the parts. Sensor shield. I hadn't checked the wiring diagram, which would have told me it wasn't usable in my situation. Non-iterative design. I hadn't tested the robot properly and built the first design I had in mind. I then had to reprint the entire robot. Modularity. I had designed the robot to have as few parts as possible. Then, when I needed to change one part, I had to take apart the whole robot. Hexapod's PCB. There was a short circuit somewhere in the Hexapod's PCB, so I couldn't upload the code when the PCB was connected to the Arduino. This made it a nightmare to code the robot. Vibrations. The servos vibrated a lot, which caused the bolt to unscrew. Compliance. The robot had no compliance, so when the robot's leg caught something, the servo broke. Upper body. I had put the cable holes in the upper body, so when I wanted to open the robot, I had to take out all the cables first. Now I'm gonna talk about what I've learned and some tips I would have used. When prototyping, design everything as simple as possible. You can improve the aesthetics and optimize once you have a working prototype. Make the design modular so you don't have to disassemble the whole robot to change a single part. Make the design expandable. For example, add mounting holes for attaching things in the future. Make it easy to access the main parts like motors and the electronics. Add a hole for the Arduino cables so you can code the robot without disassembling it. Don't print in ABS if you don't have a printer for it. Use thread locker to prevent bolts from getting unscrewed. Make a voltage reader for your battery first so you won't destroy it by draining it. Make custom PCBs. You'll save yourself time and have the electronics more ordered. Don't buy the cheapest solder. You'll save time and energy. Also use flux and helping hands. Make the code easy to read. Use commands a lot. Use functions, don't repeat code. Give variables and functions meaningful names and explain them in comments. Document the code. Write roughly what the code does at its beginning or in a text file. I've learned a lot and will definitely make a video in the future to finish what I wasn't able to this time. But now I want to make a different robot and work on my other projects. The Hexapod ended up costing about $300 to $400. All the parts are in the description. Tell me what you think about this video. Was it too long? Did I explain something poorly? Let me know. Thank you for watching and I'll see you in the next one.